Bismillah ar-Rahman ar-Rahim. Assalamu alaikum and good afternoon, everyone. I am Dr. Rami Sulaiman, a research scientist at the Interdisciplinary Research Center for Advanced Materials. I would like to welcome you to this forum organized by my center and focuses on a very important topic related to the ongoing research towards exploring various innovative solutions for material degradations. I am the moderator of today's events, and before we start, I would like to point out that this event is recorded, and the recorded event hopefully would be publicized and shared with you by the KICS office at KFUPM soon. It will be available on various KFUPM social media accounts. I would like to thank my colleagues in the center and also my colleague in the KICS office at KFUPM for their valuable time and efforts during the preparation for this event. This forum contains 5 presentations by prestigious speakers. It will be followed by a panel discussion session. The duration of each presentation will be around 30 minutes, followed by a 10-minute question and answer session. I ask the respected attendee to either send their questions to the speakers in the chat room, or they can ask the presenter right after he has finished his presentation by raising their hands. Let's put all efforts not to stop the presenter during his presentation. Okay, let me start by asking Dr. Ahmad Sorour, the director of the Interdisciplinary Research Center for Advanced Material at KFUPM. He is also an assistant professor in the Mechanical Engineering department. Dr. Ahmad completed his PhD in the Department of Material Engineering from McGill University in Canada in 2014. He has his bachelor degree and MS from KFUPM, and his research interests cover coating, typology, high temperature, corrosion, material characterizations, and metal matrix composites. The floor is for yours, Dr. Ahmed, to give your opening remarks.
Okay, thank you, Dr. Rami. Dear distinguished speaker and all participants, on behalf of the Interdisciplinary Research Center for Advanced Materials, it's my pleasure to welcome all of you to this forum titled Innovative Solutions for Materials Degradation. This new center was established recently and aspires to be a leading national center recognized globally for impactful research in advanced materials that lead to innovative and practical solutions for the national economy, society, and security challenges, as well as global grand challenges, such as one, for example, to increase the utilization of polymer and polymer composite by lowering the cost of expensive polymer composites and reducing flammability, toxicity, and cost of polymers. Another challenge like reducing energy and fuel consumption, as well as CO2 emission by, on one hand, to take advantage of new surface material and lubrication technologies to reduce friction and wear. On the other hand, to reduce the vehicle and drones weight using light material, light alloys like magnesium, aluminum, titanium based, or cost-effective polymers and composites. The third challenge, to reduce residual waste for a genuine circular economy by turning waste into higher value material, by making polymer more biodegradable, reusable, and recyclable, increasing utilization of sustainable material and replacing harmful materials. And the last challenge, which is our topic today, is to reduce material degradation, such as corrosion, wear, fatigue, radiation effects, UV embrittlement, and acid attack, to withstand harsher conditions, to extend product lifetime and durability, decrease maintenance cost, and improve the sustainability and reliability of equipment, facilities, and processes. Since time, ancient humanity has continuously struggled against the environmental impact on the performance of tools, components, and equipment. There are words such as worn out, rusted, burned up, failure, etc., are means by which humans have expressed the different forms and degrees of material degradation. The last decades have witnessed a significant increase in material degradation, which has led to significant economic implications to keep an acceptable performance level of components and facilities for a longer time. For example, the direct cost of corrosion in Saudi Arabia has been estimated to be approximately $25 billion per year. And the figure for the global cost is about $2.5 trillion per year. So a similar cost implication is associated with other forms of material degradation. This technical form is an element of the effort of the Advanced Materials Center at KFUPM to allow the exchange of knowledge on innovation solution. I take this opportunity to welcome our experts from various backgrounds to explore the theme of this technical forum. I also would like to express my appreciation for the steering committee's members and KIC's team who organized this forum online. I'm looking forward to an enlightening and informative forum. After the presentation, we have 5 presentations today. There will be a panel discussion where the experienced panelists will discuss questions related to the economical and technological implications of material degradation. Finally, thank you all for attending this technical forum, and I wish everyone a thriving forum and a fruitful exchange of ideas.
Thank you very much, Dr. Ahmad, for the excellent opening remarks. Let's move to our first pioneer scientist, Professor Philippe Marcus. Professor Philippe is the Director of Research at CNRS Center National de la Recherche Scientifique. I hope my French, I'm not destroying the French, accent. And also he's the head of the research group of physical chemistry of services of Institut de Recherche de Chimie Paris. Professor Marcus received his PhD in physical science from University of Paris and Marie Curie, Paris, France. His field of research is surface chemistry, surface electrochemistry, corrosion science, with emphasis on the understanding of the structure and properties of metal and alloys and tin oxide layers. His CV is long. Professor Marcus has published, over 500 papers, maybe more, in scientific journals, books, and conference proceedings in the area of surface chemistry and electrochemistry, surface analysis, corrosion science, and material science. The floor is for you, Professor Marcus, to start your presentation.
Okay, thank you very much. First, let me say hi, everyone, and thank you very much to Dr. Rami and to Dr. Ahmad for inviting me to this forum. It would be a pleasure to be with you. Of course, it would have been nicer to meet you in face-to-face, in person, but considering the situation, Zoom meetings are okay. They have become part of daily life. Let me share my let me share my screen.
I stopped sharing. You can share
okay,
now.
Yeah, that's fine. Okay, and let me put it in full screen.
Excellent.
Okay, so I'm going to talk about materials degradation and especially looking at this problem at the nanoscale, and at different stages of the talk. I will mention what kind of engineering technology or solutions can be found. Also, the talk is more focused on understanding phenomena, but I believe that understanding phenomena is a prerequisite to finding solutions. So I said, I'm located in Paris in the CNRS and Chimie ParisTech lab. What I'm going to talk about today needs maybe a short explanation of the background. Corrosion-induced failures of materials are observed at the macroscopic scale, obviously, but corrosion processes are surface processes, and they take place at the nanoscale, and even they initiate at the atomic scale. And for this reason, understanding corrosion of metal surfaces at atomic or nanometric scale is a key to a better design and improved control of engineering metals and protective coatings. So in this talk, I'm going to focus on a surface science approach of corrosion and protection of metals and alloys. And the topics I'm going to address are listed here. I will talk about key factors for the stability of surface oxide films on metals and alloys. Then I will switch to the key features of organic molecule oxide metal interactions for corrosion inhibition. And the last short part, which I may skip depending on time, would be on a corrosion inhibition of partially depassivated surfaces that we model by DFT calculations. So all of the data presented today are based on the use of advanced surface analytical techniques, which are combined with electrochemical measurements and in many cases combined with DFT modeling and simulation. So in a general way, surface oxides and passive films are very important because they cover the metal substrate, and in many cases they protect the material against corrosion. And these films are extremely thin. They are usually consist of an oxide and oxyhydroxide. And their stability is of primary importance for many metallic materials. And the key factors are listed here: the oxide structure, the surface hydroxylation, the interface structure, the effect of potential and time on the structure, the nature of defects and the ion transport into the oxide, the role, of course, of alloy elements, the local electronic properties, the localized corrosion initiation sites, and if the passive layer is not good enough, we need organic molecules to inhibit corrosion. So these are key factors for the stability. All of them are important and all of them require fundamental studies. I'm not going to cover all of them, but I'm going to cover a number of these points. And to look at these problems, we need methods for the characterization of metal surfaces, oxide films, and corrosion processes. We need high resolution methods if we want to understand the initiation of corrosion. If we want to have a high image resolution, we use scanning tunneling microscopy. If we want to have in-depth resolution near the surface, we use time of flight secondary ions mass spectrometry. If we need to have a good chemical state resolution to investigate the nature of surface oxides or surface compounds, we use X-ray photoelectron spectroscopy. If we want to have mass resolution, which is very important if we study molecules at surfaces like organic inhibitors, we are using, again, time of flight secondary ions mass spectrometry. And as I said in the introduction, we combine these techniques with electrochemical measurements and in many cases with DFT calculations. So among these techniques, I will show results that were obtained using scanning tunneling microscopy. So a brief reminder, in this technique, we bring a metallic tip close to the surface, and if the tip is close enough, electrons can tunnel from the tip to the sample or from the sample to the tip. And then we scan the tip along the surface. So we measure maxima in the tunneling current, which correspond to the position of atoms. So we can get an image of the topography of the surface with atomic resolution. And of course, we can also get an image with lower resolution. But atomic resolution is currently obtained. And this can be done in vacuum, in gas, or in a liquid. If we use a bipotentiostat, we can do electrochemistry. And at the same time, we can scan the tip and observe the surface with high resolution. I'm going to show some results that have been obtained in the recent past, and then show you what are the current problems on passivity of metals and alloys studied at the atomic or nanometric scale. I will show just 3 examples. Copper 111, which is a single crystal to avoid the effect of grain boundaries, which we investigate in other studies. We can, at the same time, draw the cyclic voltammogram, and at the same time, we can observe the surface in situ in the electrolyte, and we can do it with very high resolution, because here you can see an image which is atomically resolved. Each of these maxima here, the bright spots, correspond to atoms. from this, we can derive a model of the surface oxide layer, which is shown here. And we can show that the oxide which is formed is very highly crystallized. It grows in a direction that is governed by the structure of the base surface. And also the oxide is covered by a layer of hydroxyl ions. And this points to the important effect of interface energy, which is minimized by this direction of growth, and the surface energy, which is minimized by the adsorption of OH. So crystallinity, minimization of interface and surface energies are keys to understand passivity. What I just showed for copper was also observed for nickel, where you see in the passive range for nickel, but now it's in acidic solution, whereas for copper, it was in alkaline solution. You have a highly crystalline passive oxide, the model of which is shown here, where you have terraces of the oxide and steps, and you have this OH layer covering the surface. And here again, there is a slight tilt of the oxide that is accommodating the mismatch between the substrate and the oxide. And this again is provided by nature to minimize the interface energy, and the surface energy is minimized by the presence of OH group. And finally, the third pure metal that we looked at, chromium, shows similar trends, crystallinity, so highly ordered layer. And from this atomically resolved image, we can derive the structure, which is the structure of alpha Cr2O3, which is the basal plane. So that's the most stable surface that is formed on chromium. So we can say that passivity is now fairly well understood at the atomic or nanoscale because it has been studied on several metals, not all of them, of course, but several metals. And some general features are expressed here. Passive films are generally crystalline. We observe epitaxial growth on metal substrates. Interface energy is minimized by the tilted growth of the oxide with respect to the crystallographic orientation of the surface, and surface energy is minimized by hydroxylation. The work I've shown was done on single crystals to get rid of grain boundaries, but obviously these conclusions can be extended for each grain at the surface. So these conclusions here are not, of course, restricted to single crystals. They would apply on individual grains of a polycrystalline materials. As for grain boundaries, there are studies in parallel because the reactivity of grain boundaries is different from the reactivity of grains. Of course, we need to know about alloys and not only pure metals. So this kind of work was extended to several alloys, and I'm going to show just the example of stainless steel, on which both on austenitic stainless steel, iron, chromium, nickel, or ferritic stainless steels, we also observed a highly crystalline layer. You can see here the very high resolution image. This is 0.3 nanometers. And again, each of these bright spots correspond to position of atoms. And this corresponds to the structure of chromium oxide, alpha Cr2O3. So the passive layer on stainless steel is crystalline. It has the structure of alpha Cr2O3. But of course, there is not only chromium in it, there is also iron in it. The other point is that the degree of crystallization depends on time. These are images that were recorded at different lengths of time, short time, longer time, and even longer time. And you can see that at the beginning, the surface oxide is completely disordered. It's amorphous. But when time goes on, we start to see small crystals, nanocrystals, because this is, again, high resolution, and this is an atomically resolved image. So nanocrystals are formed, and gradually the crystallinity extends, and the whole film becomes crystalline after long enough. And we have shown in some other works that the time of exposure in the passive region provides better resistance to localized corrosion in chloride solution. And this is due in part to the enhanced crystallinity that is demonstrated on this slide. The other factor being the enrichment of the passive layer with chromium. So chemical effect is of course very important. An oxide rich in chromium has a better corrosion resistance than an oxide that has less chromium on stainless steel, but also the extent of crystallinity is a critical factor. So that is where we stand. And of course, there is still something that we need to understand better in terms of corrosion resistance and also in terms of how can we improve the corrosion resistance of stainless steels, which is already quite good, but however, stainless steels are not perfect. So this is what I'm going to talk about briefly now. Stainless steels are normally well protected against corrosion by passive films, but however, there are weak points that can lead to passivity breakdown and localized corrosion. And the exact nature and origin of these weak points is not known. Of course, we know that if there are inclusions like sulfide inclusions, pitting will start at inclusions. But in very pure stainless steel, and modern metallurgy produces fairly pure stainless steels, there are still weak points in passive layers, which are not just sulfide or other inclusions. So the fundamental scientific questions that we need to address is also, can the oxidation process itself produce weak points in the passive film? In other words, even in the absence of inclusions or structural defects, are there processes that can create the weak points during the oxidation of the material? And of course, to study that, we need very advanced techniques. And this is what the equipment we have been using now for a couple of years. It's a new platform that integrates multi-technique and environmental tools for spectroscopic, macroscopic, and electrochemical analysis of surfaces. So this is a sort of unique equipment in which we can prepare surfaces under gas or in UHV conditions. We can do thermal treatments, and we can transfer samples in the different parts of this equipment. In one part, we can look at the structure by scanning tunneling macroscopy in a variable temperature system, so we can vary the temperature. We can also expose the surface to gases. In another part, we can do in situ XPS, that is, we can do XPS in the presence of gas, and we can make real-time measurements of oxidation in a gas environment. And finally, we can transfer the samples inside this equipment to a glove box in which we can do some analysis of the solid-liquid interface, and there is an electrochemical scanning tunneling macroscopy. So it's a sort of material science or surface science lab in which we can do surface preparation, heat treatments, exposures to gas and liquids, and analyze the surface chemically and structurally without exposing the surface to air. So we can look at the very initial stages of reactions, which I believe govern the life. A good part of the life of a material is what happens in the early stages remains a major feature, a major ingredient to understand the life of a material. So with such an equipment, we can prepare very pure, very clean surfaces like what you see here. It's the surface of stainless steel. It would be an austenitic stainless steel. And you can see by looking at the XPS that it's extremely clean. There is absolutely no oxide. This is the iron signal here. And this is here the chromium signal. We don't show nickel because nickel is anyway not oxidized. But you see that it's a purely metallic surface. And we can look at the surface by STM, and we see this interesting structure with terraces and steps. And we see that under equilibrium, there are vacancies at the metal surface. This is a completely new finding because people saw that if you had a clean stainless steel surface, you would have no vacancies. But this is not the case. there is a network of vacancies. You can see that these vacancies are aligned in well-defined direction. So now with such a very clean and well-defined surface, we can look at very early oxidation stages, and we can look at oxidation as a function of exposure. And this was done in that case at 250 degrees in low oxygen pressure so that we have time to follow the phenomena. And this can be done in the XPS, and we can measure the oxygen signals while the material is being oxidized. So we can look at exposures that are very low. Just a reminder, 1 Langmuir is an exposure that is 1 second at 10 to minus 6 millibar of pressure. That's the Langmuir unit in the international system of units. So looking at this scale of time at low pressure is equivalent to looking at just the first few nanoseconds of oxidation at ambient pressure. So that provides a way, a unique way to look at the nucleation and growth of oxides, in that case on stainless steels. We can see that we have first a striking enrichment of chromium at the surface, then it goes down because iron starts to be oxidized. So this is the XPS. Now we can look at that at the same time by scanning tunneling microscopy. And this is a high resolution image before oxidation with a very clean surface and these rows of vacancies. And when we expose this surface to oxygen, you can see these small islands here, which are nuclei of oxides. And you see that they form at the step edges. They don't form at the surface. So the initial oxidation takes place preferentially at the step edges. And we could assign this to chromium oxide nuclei because we know from XPS that at the beginning only chromium is oxidized. So that allows us to propose a model for the early oxidation in which this is the initial stainless steel surface. This is a terrace, and these are steps between two terraces. As you can see, we observe multi-atomic steps, and after exposure to oxygen, only the step edge here is covered by chromium oxide nuclei, and it's pure chromium oxide, meaning that chromium has been diffusing on the surface to the step edges. And of course, this means that there will be a depletion of chromium near the step edge. This is also confirmed by the fact that we find a new distribution of vacancies. These are the vacancies on terraces after short oxidation, and the distribution of vacancies has been changed due to the role of vacancies in the transport of chromium to the step edges. We believe that this is a major observation because we can predict that there will be an area here and near the step edge where chromium concentration will be lower. So what will happen there? Then if we continue the oxidation and look at a slightly longer exposure, then if you look at the STM image, you can see that now the terraces are also covered by oxide, which have the same structure as at the beginning. So these are chromium oxide islands, but we have other features that are near the step edge. And if we look at them in details, they are shown here. They are consistent with the formation of iron oxide rather than chromium oxide. So this is the model here. At the beginning, we have formation of chromium oxide. So we have depletion of chromium in this area, and that's where iron oxide will then form just because the chromium concentration has been decreased. And we believe that these areas will be weak points for the corrosion protection by a surface oxide. And we did some now experiments in an electrolyte, and this is, so this, I should conclude there that this is the way the weak points are created by the oxidation process itself. So now if we look in an electrolyte, this is an in situ image of a stainless steel. In that case, it's a 316 stainless steel. And you can see that you have these small depressions here, which we believe would be where pits would propagate if we had conditions that would produce pitting. And you can see that these depressions are not localized at the step edge. The step edge is here, and that's where we have an enrichment of chromium oxide. But these depressions are localized on terraces, and we attribute them to these weak points that are formed by the corrosion, by the oxidation process itself. Which means that in the future, we will have to find ways to heal this defect. So this opens the way to, I think, a wide range of nano-engineering that we and other labs are now exploring. So how to heal these defects that are these chemical defects that are created by the oxidation process itself, that are independent of the presence or not of inclusions. Okay, let me now move to another part of this talk, which now I'm switching to corrosion inhibitors. Why inhibitors? Well, for obvious reasons, surface oxides are not always protective enough, so that in that case, there is a need for surface treatments that can include conversion coatings, but also corrosion inhibitors. So there is a fairly intense activity in my lab, but also in many labs, trying to find new corrosion inhibitors, in particular for aluminum. And I think a rational search must be based on a combination of surface analysis, corrosion test, and DFT calculations. So what I'm going to show now is part of a European project on which the name was Core ID, and the idea was to find new corrosion inhibitors on a rational basis. This was a strong collaboration with a group in Slovenia, in Ljubljana, headed by Professor Milošev, and also Anton Kokaj, who is also doing DFT calculations. So what is the aim of this approach? Well, this is shown here in the background. If we want to provide corrosion protection with organic inhibitors, we need to look at the affinity of organic molecules with the surface, which is, in the case of aluminum, an hydroxylated aluminum surface. So what do we want to understand? We want to decorrelate or disentangle the role of the anchor group on the corrosion inhibition and the role of the chain. So what we did here is we were looking at these two key factors: the effect of the type of anchor group for a given length of alkyl chain, or the effect of the chain length for a given anchor group, because both this anchoring group and the lengths of the chains are important. So I'm going to show a few results where, for example, we looked at carboxylic acids with a different number of carbons in the alkyl chain, and then we looked at a fairly wide range of anchor groups here for the same alkyl chain. So let's start with looking at the effect of the chain length. We did that on on an aluminum surface. In that case, that was pre-treated so that we have a rough surface which is formed. Then we expose the surface to an ethanol solution containing the organic inhibitor. We analyze the surface by surface analytical techniques. Then we expose the surface for 6 months in chloride solution. And again, we perform surface analysis. So we can combine a corrosion test and surface analysis and try to understand what are the key factors for the choice of good corrosion inhibitors. So to do that, we used XPS. So I think you all know the principle of XPS. We use an X-ray source photoelectrons are emitted, and we analyze the energy and measure the number of electrons, so we can get an insight on the organic molecule layer, the nature of the oxide under the organic molecules, and the base metal. And this is the equipment that we are using in my lab. This technique is quantitative, meaning that we can not only identify the nature of the surface species, but we can also calculate their concentration. We can also calculate the thickness of the organic layer, the thickness of the oxide. So it's an extremely high efficient technique. We also use time of flight SIMS, which in general for corrosion research, and in particular here for looking at corrosion inhibitors. And this is the principle. Here we have a beam of primary ions that are hitting the surface. Secondary ions are emitted and analyzed, and this analysis provides a mass spectrum in which we can detect all the masses and all the elements at the surface. We can combine this with a second beam to make in-depth profiles. And this is the equipment that we are using in my lab. So first, we looked at absorption of octanoic and stearic acids, and the XPS is telling us that both organic inhibitors are adsorbed at the surface. We can state that by looking at the carbon 1s signal. And from the aluminum and the oxygen, we can also derive the chemical states of the aluminum, the amount of oxide and hydroxide. So the conclusion here is that both the octanoic acid and the stearic acid are observed at the surface. However, if we look at the quantitative results, we find out that the coverage is different, and that the only stearic acid gives a complete layer of organic molecules. The coverage obtained with octanoic acid is lower than the one obtained with stearic acid. If we look at the time of flight SIMS, so these are mass spectra obtained, the top row for just the aluminum, the reference, it's the blank experiment. Second row, that's after exposure to octanoic acid, and third row after exposure to stearic acid. And you see that, for example, if we look at the mass of octanoic acid, there is a clear signal after exposure to this inhibitor, but no signal in the other case. So we can conclude that there is indeed adsorption of octanoic acid in this, and this is in agreement with the XPS. Similarly, for the stearic acid, we observe a significant peak at the mass of stearic acid. So this confirms what we have observed by XPS. With TOF SIMS, we can get an additional measurement, is that we could look at fragments of the molecules that contain aluminum. Here we looked at a fragment containing one aluminum atom, and here we looked at fragments containing two aluminum atoms. And you can see that if you look at the octanoic acid, we find signals for fragments containing one aluminum and containing two aluminums. And this is also the case for stearic acids. So we can conclude here that the inhibitor is bonded to one or two aluminum atoms. And this is, of course, a key feature is the nature of the chemical bonding of the organic molecule to the oxidized surface. Now we look here at the surface after immersion in sodium chloride for 6 months. And you can see that for both octanoic and stearic acid, there is still a signal associated to the organic acid, which can be observed by looking at the high binding energy where we observe the carboxylate group. So in both cases, the molecules are still there. However, there is also some surface contamination in addition to the presence of the organic acids. Now we looked at the nature of the carbon chain for some other molecules, octyl benzoic acid, and we also looked at perfluoroinhibitors for comparison. So to make a long story short, we look at the fluorine 1s spectrum for the perfluoro molecule because it's a very good marker of the presence of the molecule. And in these three cases here that I'm showing with my pointer, you see that we have a fairly intense fluorine 1s peak, which means that all these perfluoro molecules are well adsorbed and bonding to the aluminum surface. And this is the case of also of this octyl benzoic acid, according to the presence of these two CO and COOH functional groups. And we can at the same time, not at the same time, but on the same material with the same inhibitors, we looked at the, we did measurements in collaboration with the lab in Ljubljana on the corrosion current. And what is shown here is the change of corrosion current provided by the molecule. So now what we are doing is we are relating the advanced surface analysis showing whether the molecule is bonded or not with the corrosion test that is telling us what is the beneficial effect of the molecule. We looked at the number of anchor groups now, looking at many different anchor groups. And what is collected here are all the anchor groups that for which the molecules was not found adsorbed. So what we did essentially for all these molecules, we looked either at the nitrogen 1s signal in these different molecules, or we looked at the sulfur 2p signals for thiols molecules. And you see that in all these cases, you can see only noise, which means that none of these molecules is adsorbed at the surface. So obviously, you don't expect that they will be good inhibitors. Now we looked at phosphonic acid, and we looked at this molecule, which is the octyl phosphonic acid, and we could clearly detect the phosphorus 2p signal both before immersion in sodium chloride solution and after immersion. So the conclusion here is that this molecule is adsorbed on the aluminum surface, and it remains adsorbed even after a long time immersion in the solution. And the same conclusion was obtained by looking at the mass spectra by TOF-SIMS, by looking at molecules that contain the phosphonic group. And we could also look at fragments containing aluminum atoms. And in that case, we could see that the molecules are bonded to 2 or 3 surface aluminum atoms, in contrast with the carboxylic groups that were bonded to 1 or 2 surface aluminum atoms. So now we can make a summary of what we have done. So in this busy table, we have here the anchor group, and we have here the alkyl chain or the perfluoro chain. In this column here, there is the result of adsorption using XPS and TOF-SIMS. And then there is here the result on the measurement of the corrosion current. So let's first look at the adsorption. All these molecules provide no adsorption. This is what I have shown in this talk. Now, these molecules, octanoic acid gives an incomplete layer, and only the stearic acid gives a complete layer. These molecules here with the benzoic acid and the phosphonic group gives complete adsorption layers. And the second column is whether we detected these molecules after immersion in sodium chloride. So obviously not in the case where they were not adsorbed from the beginning, but in these cases where you have the yes in red, we would expect if we have adsorption and even detection after immersion for 6 months in chloride solution, we would expect an effect on the corrosion inhibition. If you look at the perfluoro chain, again, there are cases where there is no adsorption if the anchor group is not good. But if the anchor group is okay, like carboxylic groups, in that case, all these perfluoro molecules are adsorbed, and they remain adsorbed after 6 months exposure in sodium chloride solution. There is an additional information, which is the nature of the bonding to the surface, which I've indicated before, could be mono or bidentate in the different cases, or even tridentate in the case of the phosphonic group. So now if we look at the correlation between these systematic study using surface analytical techniques and the corrosion measurements, this is shown here. Now you have to look at what happens in terms of corrosion current when you have, yes, there is adsorption, and yes, adsorption remains after exposure to the chloride solution. And this is the number by which the corrosion current is divided. And you can see that there is a very big effect when you have these two yes in red. Here it's divided by 45, 35, 40, 21, 53, 45. So there is a very strong effect and a very good correlation, the direct correlation between the key feature, which are adsorption, nature of the chemical bond, and effects on corrosion. So just to summarize, and because time is running, let's move directly to the two conclusions here. The molecules with thiol, azide, cyano, and disulfide function are not adsorbed, and as a consequence, they have no inhibiting effect. The best inhibitors are the carboxylic acids with a long aliphatic chain, and the perfluoro chain, and also phosphonic acids. So this systematic study allowed us to select what are the best corrosion inhibitors. So again, there's a direct link, in my opinion, between studies that are performed at the molecular level, so it can be atomic level or nanometric level or molecular level, using the techniques that I have shown today, and the possibility to design new corrosion inhibitors, as well as the possibility to do some nano engineering of surface oxide. So I strongly believe that looking at surfaces at high resolution at the nanometric or molecular scale is necessary, and will be more and more necessary in the future to design the mitigation measures to lower degradation of materials. Okay, I think my time is over, so I will skip the last part, which was on DFT calculation, but there will be a talk later today on DFT. So DFT will clearly be represented in this symposium. So just a general conclusion that significant progress in understanding surface corrosion processes at the nanoscale, and I should say also at the nanometric and molecular scale, and that included passivation and inhibition. And that can be achieved by a surface science approach in which the surface chemical and structure characterization is combined with electrochemical measurements. And although I have not shown that today due to lack of time, this is very often combined with modeling and simulation. And the reason is that the experiments we are doing, being at the nanometric or atomic or molecular scale, they can be directly translated in DFT. And that's very important because it may be shown later, but it is very important because when you choose the model in DFT, you need to have experimental results to choose the right model. And as our experiments are done at the same level in terms of dimensions as DFT, we can use the measurements to start with the right DFT model. So finally, I re-emphasize that the mechanistic understanding opens the way to, say, nano-engineering of surface oxide layers, how to seal the defects now that we know what they are, and also a rational design of organic inhibitors and not just a try and error approach of organic inhibitors. And with that, I would like to thank you for your attention. And this is just a picture of my group in Paris, the Physical Chemistry of Surfaces research group. So this was in the pre-COVID time where we can meet without wearing facial mask, and hopefully we will return to this time in 2022. And I would like to also acknowledge for funding the European Research Council as part of the Horizon 2020 program, and also the Région Île-de-France for providing funding for the major equipments, STM, XPS, and those things. So thank you again for your attention.
Thank you very much, Professor Philippe, for the excellent presentation. And I was really sorry that your time is over. I think we have only one time, so to follow the schedule, we have time only for one short question. If anybody would like to ask, please raise your hand, and maybe you can unmute yourself and ask. Any question, gentlemen?
Yes, I have just
Please.
one for Professor.
Yes, please.
Yes, in the area of inhibitor, yes, this is a fundamental study, which is very important. But I want to look at the for industrial application. For example, you are using aluminum as the metal. So which industry is this kind of and then you use a sodium chloride environment. So and 0.6 molar. Which industry is
Yeah. Well, of course, this is one brick that you need to build the wall. So I have today shown what we are doing on aluminum. We are doing something similar on copper, and actually the DFT I was going to show was on copper. And then obviously we are doing a lot of work more applied, but I wanted to show you the fundamental work.
Sure,
the more applied work we do essentially on aluminum alloys, and we have a lot of connections with the aeronautic industry in France. So we have research contracts with the aeronautic industry, and so we look at the alloy 2024, where the main problem is, of course, how to inhibit corrosion where we have intermetallic particles. And the intermetallic particles are rich in copper, but they also contain aluminum. So the approach is a step-by-step approach, going from model systems like pure aluminum, pure copper. We have also worked, and we have published some papers on the on compounds that we synthesized that have the same composition as the intermetallic particles. So for example, Al2Cu, which is the main intermetallic particle in alloy 2024. And then we also work on just the real alloy. So of course it's very ambitious, because we start from simple model systems, but we try to go all the way to the alloys, and in particular alloy 2024 for the aeronautic industry.
Okay, excellent work. Thank you.
Thank you.
Thank you, Dr. Ime. I don't know, can you, Professor Philippe, can you see the chat, the questions? Because I think we have to move on. Maybe you can reply them during the panel discussion or later. But gentlemen, to stick to the time, we have to move on to the next presentation.
Okay, thank you again.
Thank you, Professor Philippe. I think we can have now 10 minutes of break, and we will resume with the next speakers at 3:30. Thank you very much. Okay, Assalamu alaikum. We are resuming again with our next speaker, Dr. Ime Obot. Dr. Ime is an associate professor, recently promoted to research scientist 1 at the Interdisciplinary Research Center for Advanced Material. He obtained his bachelor in applied chemistry from the University of Oyo, Nigeria, in 2003, and his master and PhD thesis in physical chemistry, corrosion, and electrochemistry from the University of Ibadan in Nigeria in 2006 and 2012, respectively. His research interests include corrosion scale inhibition, sweet corrosion, sour corrosion, microbial influence corrosion, molecular engineering, chemoinformatics, modeling, corrosion cooling water systems, high temperature acid corrosion, and computational chemistry. The floor is yours, Dr. Ime, for your presentation.
Thank you so much, Dr. Rami, for a wonderful introduction. And thank you for the team and for inviting me to give this talk. And welcome to this presentation. So we'll discuss briefly on some 5 areas: material degradation due to corrosion, corrosion inhibitors, what are the fields of application, and I will talk about corrosion inhibitor laboratory development and past and current approaches. And I will also go into corrosion inhibitor development, the future approach. Then finally, we will look at future challenges for corrosion inhibitor development. So I will begin by looking at material degradation due to corrosion. So as you see in this slide, corrosion is the deterioration of a material, usually a metal in this case, although non-metals like non-metallics can also degrade, but here we are concerned about metallic material. This is as a result of chemical or electrochemical reactions between the materials with this environment. So this is according to NACE STMG 193 definition. So as you see here, corrosion causes material degradation. So from shapes to pipeline to automobiles, to military equipment, to towers, oil and gas pipes. Corrosion is a cancer for metals. There are a lot of consequences and a lot of impacts of corrosion. So first of all, look at the consequences. So these are images of some of the consequences that was due to corrosion. So we have in Belgium in 2004, so there was an explosion of pipeline due to corrosion. In southern Taiwan in 2014, there was also explosion due to corrosion. So corrosion has a lot of safety, environmental consequences. And there are a lot of impacts from energy and fuel infrastructure to health and safety, national treasures and artifacts, national security and readiness, environment, even critical infrastructure, and economic security of any nation. So corrosion has a lot of impacts, and that is why we try to find solution to this menace. The cause of corrosion globally, we have heard this before, is in a study by NACE 2016 study. The total cost amounted to $2.5 trillion US, which is 3.4% of the global GDP of developed nations. And it has been estimated that about 375 to 875 billion US could be saved using proper mitigation approaches. So if we move to the Middle East, the Gulf region, we found out that among the Middle Eastern countries, Saudi Arabia has the highest cost of corrosion, amounting to about close to $25 billion US. So this study was conducted in 2011. So generally, I want to take you to understand a broader field of applications of corrosion inhibitors. Corrosion inhibitors are applied in a lot of fields. So this is not exhaustive. There are a lot of many industries which I have not listed here, but briefly, it can be applied in cooling, industrial cooling waters. In the military, the military assets require protection using corrosion inhibitor, marine environment. In the power plants, we are talking about both thermal power plants, nuclear power plants, even renewable like geothermal plants. So all these plants are constructed using metals, and they are prone to corrosion. And corrosion inhibitor is one of the solutions to mitigating this corrosion. In the automobile industry, corrosion inhibitor is very vital. In the construction industry, in bridges, in the steel rebar, in concrete, it's important to apply corrosion inhibitors. In oil and gas, both upstream and midstream, and in the downstream, in the refinery operation. So you see, even in the aerospace, it is like Professor Philippe Marcus presented, corrosion inhibitor is very, very useful. So that is why it is one of the important solution for corrosion mitigation. But in this talk, I will zero down to only oil and gas industry, and I will only talk about the upstream and the midstream. So for the oil and gas industry, we have the upstream, which is oil and gas exploration and production. We have the midstream, which is transport and storage. And then we have the downstream, which is refining and distribution. So my focus here will be just the upstream and the midstream. We want to see corrosion inhibitor development in these two areas. So what are the corrosion challenges facing the oil and gas industry? So as you can see, they are enormous. So we talk about CO2 corrosion, the so-called sweet corrosion. We talk about H2S corrosion, the sour corrosion, which is prevalent in this region, the Gulf region, mostly sour crude. We talk about acid corrosion during acid stimulation of the well, acidizing processes, oxygen corrosion during drilling operation. So high temperature, high pressure corrosion. This is for deeper wells at high temperature and high pressure can be encountered. So this type of corrosion is common. Microbial influence corrosion, MIC, and then localized and erosion corrosion. Then we have top of the line and under deposit corrosion. So you see there are a lot of corrosion issues facing the oil and gas industry. So here you have some of the examples of oil field corrosion. So starting with top of the line corrosion, that means corrosion at the top, especially 10 to 2 o'clock position of the tubing here, where normal corrosion inhibitor at the bottom of the well cannot really protect the top. And then we have some of the degradation due to CO2 corrosion here. And H2S corrosion, you see formation of the iron sulfide, which is black, normally black in color. We also have corrosion at the preferential wells. And pitting corrosion, which is one of the severe damage. General corrosion is not really very important, but severe damage, localized corrosion due to pitting is very difficult to mitigate. Erosion corrosion due to wear or flow. Under deposit corrosion formed due to formation of scales on the pipe. And then the microbial corrosion, which is very, very important too, due to reduction of sulfate, to sulfur by sulfate reducing bacteria. So in the oil and gas industry, these are the proportion of failures that are normally a weakness, and the causes of the failures related to CO2 corrosion is up to 28%, and hydrogen sulfide corrosion 18%, preferential well corrosion 18%. So you can see that the first four CO2 corrosion, sour corrosion, preferential well corrosion, and pitting constitute the majority of the failure that normally happens in oil and gas production. But that does not mean that erosion, galvanic, crevice impingement, and stress corrosion cracking is not also common. So, but the major problem is normally related to sweet corrosion, and sour corrosion, and pitting, and preferential well corrosion. So what are the corrosion control methods? So basically in the oil and gas industry, there are several ways of, and several solutions of mitigating corrosion. So you can see from material design to give corrosion allowance, to corrosion resistant alloys where you cannot use carbon steel, to cathodic protection system always coupled to surface coating, and using a chemical treatment called corrosion inhibitor. So here I will focus on the corrosion inhibitors. So first of all, let's look at the corrosion inhibitor market. Globally, you see that in this analysis that was published by Saudi Aramco, it was found out that almost 45% of the market is controlled by two oil field chemicals, emulsifiers and corrosion inhibitors. And corrosion inhibitors globally is up to 20% of the global market. In the Middle East region, we found out that about 60% of the oil field chemical market is also controlled by emulsifiers and corrosion inhibitor. So corrosion inhibitor also takes about 21%. So it shows the importance of corrosion inhibitors in the continuous survival of oil and gas production. So what is here, remember here I'm focusing on oil field corrosion inhibitors. Corrosion inhibitor is a chemical compound that when added to a liquid or a gas phase, normally decreases the corrosion rate of the material. Here, typically, we are looking at the metal. So here, they act by forming a film, thin barrier layer between the steel surface and the corroding fluid. So normally, it works by chemisorption mechanism, where there is interaction between the molecule and the metal surface. Normally, they are applied in ppm levels, and for oil and gas application, they are normally complex mixtures. So they are not like a single molecule. So they are formulated into using different combinations of chemicals. So here I'm giving you the general classification of corrosion inhibitors. So we have inorganic. Inorganic are mostly toxic. So toxic inhibitors, and inorganic are classified into anodic, which can be oxidizing, and non-oxidizing, like chromate is oxidizing inhibitor. We also have cathodic inhibitors like phosphate, and they work by precipitating on the metal surface. We also have environmental conditioners or scavengers. So these changes the pH of the environment and also can scavenge corrosive molecules and ions like H2S. We also have organic corrosion inhibitors, and primarily they work by affecting both the anodic and cathodic reactions. So, and mainly they are film formers. And this class of corrosion inhibitors, some of them are toxic and some of them are non-toxic. And these are the class of inhibitors which are normally used in the oil and gas application, the film forming type. So in the oil and gas industry, corrosion inhibitors are classified into film forming, oil soluble, water soluble, oil soluble, and water dispersible. So all these classes are classified based on their application. For example, film forming, they will form a film on the surface and they will wet the surface and form hydrophobic layer on the surface, mainly effective for CO2 and H2S corrosion. Oil soluble, they are normally used for lower water cut and very effective for stratified or turbulent flow regime. For water soluble, this is normally used when you have higher water cut and then can be effective for stratified or turbulent flow regime. Then when you have oil soluble water dispersible, so this can be used with all water cuts, and then this is mainly a kind of inhibitor that can partition between the oil and water phase. So here we have some typical examples just to take you so that you can really see some of the examples of corrosion inhibitors. And this diagram, you see how it works. So you have the hydrophilic end. This end can bind to the metal surface. And then you have the long alkyl chain ends. So this end will form the hydrophobic film on the metal surface and then displace the water from the surface. So these are some of the typical examples. Like typically in the industry, they use imidazolines, amides, alkyl pyridines, phosphate esters, quaternary compounds. And then they also use some solvents and surfactants. So basically, how does corrosion inhibitor works? So normally you have the surface of the pipe, you have the active group, which is the hydrophilic group that binds to the metal surface. You have a lot of CO2, water, H2S, and then you have salt, what we call brine water. So what the inhibitor does is to use the active head and displace the water from the surface and attach to the pipe, whereas the hydrophobic group here will displace the water and then make the film, form a film, a thin film on the surface of the metal. So there are a lot of factors that affect the performance of corrosion inhibitor in a typical oil downhole tubing or transportation pipe. So for the downhole wells, we know temperature is very critical. So sometimes the temperature can go up to 300 Fahrenheit. So sometimes more, especially when you are dealing with the deeper wells. We have very high sour systems, greater than 20% H2S. So this will affect the performance of corrosion inhibitor. The presence of solids in the tubing, velocity, and this is very important because if you have very high flow rate, your inhibitor might not withstand very high shear stress. Another important factor is incompatibility with other production chemicals. Normally in the oil field, we have other production chemicals like KHI, scale inhibitors, biocides, and many more. So you have to make sure your corrosion inhibitor does not affect the performance of other oil field chemicals. We also have very high TDS in some applications, very high TDS, up to 200,000 ppm of brine. So this will affect the performance. pH changes, brine compatibility, presence of scales, presence of elemental sulfur. For example, in this region, we have high sour condition. So elemental sulfur can be produced, and this will affect the performance of your corrosion inhibitor. So here I want to describe corrosion inhibitor laboratory development, the PASS approach. So here, the normal selection is done by, first of all, selection of hundreds of active chemicals, normally done by trial and error. So what happens is that many active chemistry are Many libraries of active chemistry are screened, and then they are tested using the so-called bubble test, just to screen them. And then after screening them, a few of them that are performing will be moved to the next stage of chemical formulation, and then they will further undergo some screening tests to select the best formulation. And then from the screening stage, you move to selection of the best formulation using a more severe condition of where we can use rotating cylinder electrode, autoclave testing. Sometimes we use a flow loop and jet impingement just to simulate very high shear stress. Then you can also carry out characterization if you want to understand whether there is pitting. You can use a surface profilometer to analyze the pitting, and also other surface characterization tool. Then to make sure the corrosion inhibitor will perform well in the field, you also do what we call secondary property testing, like thermal stability, emulsion, foaming, film persistency, partitioning. And then you also, for application like offshore, you have to be sure that your inhibitor will be non-toxic to meet some strict environmental guidelines. So basically, you employ a lot of standards, STM, G1, 31, 46, 59, 102, 106, a lot of them. And you use several equipment. So this is very capital intensive. And you spend a lot of time testing, screening, before you could even get one final product. Now we have a current approach, which we currently use in our center here, and some people have started using it too. Many people are already using it also, like we saw in the presentation by Professor Marcus. So first of all, you could deploy computational screening and a computational tool to select your active. And then you could, because this will save a lot of time, because instead of testing randomly, trial and error, just selecting several chemistry, testing them at random, you could use this tool to first of all, limit the number of active that you test. Then you can move on to validation of the best active. From there, you go to chemical formulation, screening testing of the formulation, selection of the best formulation using more aggressive conditions like autoclaves and maybe high shear conditions. Then you could do pitting analysis and secondary property, and you still go to your final inhibitor, corrosion inhibitor product. But here, mind you, you will still use a lot of standards. So this is, although it is capital intensive too, but it gives you a faster approach to select your active ingredient. So I would describe briefly the computational designing approach, and then and then I will give you an example of one of the projects that we did, which we started by using the computational approach. So here we have some facilities that helps us in this computation. We have Material Studio software, which is very, very excellent for DFT calculations and molecular dynamic simulations, Gaussian software for DFT. We also have a Spartan software, which is very accessible for calculating chemical properties of molecules, which is very important too. And also we recently acquired this software, Perceptor, which is good to predict toxicity of molecules and some physical properties of molecules. Here I will explain to you, the typical approach, how this computation works. There are a lot of properties of molecules. Normally, molecules work by, if you know their physical properties, their chemical properties, you can determine the application of a molecule. So if you select a molecule, first of all, what do? You could compute the physical properties, toxicity properties, such as lack of hydrophobicity, which gives you whether that molecule will form a film on the metal surface, solubility, which is very important in corrosion inhibitor selection, because you have to know whether your molecule will dissolve in the water phase or in the oil phase. This is very important because it's difficult to it's more extensive to test the solubility. So we could predict solubility of these organic molecules. We can determine the molar volume, the pKa, which is very important, describing the electronic donor ability of your molecule, because your molecule must donate electrons to the metal to bind or to chemisorb on the metal surface. And also we could predict acute toxicity. So these are just a few properties that we could predict using this perceptor. We could also look at the interaction of the molecule with the surface of the metal at the atomic scale using quantum mechanics, which we call DFT calculations. It can furnish us with absorption energy and some electronic properties of the molecule surface interaction. So this can be like a property of the molecule, like the absorption of the molecule on the metal surface is very important for corrosion protection. So if you could determine the absorption energy of the molecule on the metal surface, it can give you a descriptor that can give you a clue of whether the molecule will inhibit corrosion or not. We could also use molecular dynamic simulation. So this is very important because corrosion takes place in the presence of aqueous environment. And in the oil field, we have a lot of brine, chloride, we have sometimes even we have organic acids. And then we have a lot of ions like carbonic acid, chloride, and so on and so forth. So we could use the molecular dynamic simulation, as you see here, to really look at the diffusion of molecules or ions across the corrosion inhibitor membrane. So this can give you a lot of diffusion coefficient constants that you can then, if you are screening like 50 molecules, it could help you to reduce the time to testing a lot of molecules by just trial and error. So we combine all these properties, and then it helps us to really screen a lot of molecules in different environments. Even if you want to use polymers, you can also look at permeability, diffusion of these small molecules on polymers. So this has a lot of applications, even for non-metallics. You could use simulation like this to study permeation of molecules on polymers. So this is very important too. So briefly, this is one of the projects that we use this tool, and we have very excellent outcome from the project. So we, first of all, we design and use computational modeling to screen about 15 chemistries. We design it from scratch. We build the chemistry from scratch, and then we compute a lot of properties. And then at the end of the day, we were able to have 8 of the chemistry that gave potential results. And then we synthesized them, about 8 of them. So, and the result was very, very good because we have them in a very good yield. Then we further go for characterization. So we did a lot of structural characterization like FTIR, proton NMR, carbon-13 NMR, TGA to test for the thermal stability of this molecule. Then we did corrosion evaluation and some of the secondary property testing. So at the end of the day, we were able to get 2 potential active candidates. So, which you see the result here. The initial corrosion rate was 140 MPY after 2 hours. And after 24 hours, the corrosion rate was reduced to 2.65, which was a very, very good result. So this is one of the examples that we've used this tool, and it helps us to reduce time and effort in in the lab, because testing in the lab involves a lot of standards, a lot of equipment. So by using this tool, it cuts a lot of time and equipment. So what is the future approach? So the future approach will be using machine learning, artificial intelligence. So the first approach is trial and error, like we said before, a lot of effort in selecting chemistries, several chemistries, carrying out a lot of testing to qualify the active component before doing formulation. So this is it requires expensive materials and equipment, very laborious, and it requires a lot of large manpower. Now, the current approach which we are using currently, computational screening, it will save costs and it will also reduce time for development, but it still requires a lot of testing, because after you do use a computational tool, DFT, to look at the electronic properties, absorption properties, and then you use a lot of computational tools to also screen or diffusion of the molecules. All these properties you still need to test to validate your result, because like I said, computational tools alone cannot validate your work. You need to do experiment just to confirm whether your result is in agreement. But in the future, I think data-driven approach will be the tool for the future, using machine learning to drive product development. So this will be cost-effective and it will require less expensive material and testing, but it will need a lot of data. So what is this approach all about? So we will collect data, experimental data, historical data, or databases from literature. So we will look at the data from the literature, or we could generate our data experimentally. And then we will only look for input parameters of the molecule. And this input parameter, we could compute them using computational tools like DFT, molecular dynamics properties, physical and chemical properties, even structural properties. So these input parameters, we call them descriptors. We could calculate them. And with your experimental data, experimental parameters that you develop over time or that you get from databases or the literature, you could do data pre-processing and you could do feature engineering, selection of the best input parameters. Then you could use any of the machine learning models to train this data and then validate your data. Some of the two machine learning algorithms like supervised learning and unsupervised learning classification approaches can be adopted. And then you could evaluate these machine learning models. So you could, after evaluation, you could deploy this model and you could predict a new corrosion inhibitor active. So I think this will save a lot of time and a lot of effort, and it will lead to faster corrosion inhibitor development. So I will look at finally the future challenges. So what are the future challenges for corrosion inhibitor for oil field application? Remember, I'm focusing only on oil field application. There are a lot of applications, like I said before, but this is just for oil field. So future challenges and research directions are like you hear from the last presenter, moving away from steel or from metallics to non-metallics. Even with non-metallics, there's a lot of problems already. And so the same thing happened with metallics currently. So there are still a lot of problems with corrosion, corrosion for downhole wells at high temperature and pressure. And we have, this also poses challenges for corrosion inhibitor. For high TDS, total dissolved solids, some of the brine can go up to 250,000 ppm. So this is very high, so it will also pose a challenge. High shear stress condition. Localized corrosion is very important because normally general corrosion rate is not really a problem, but localized corrosion is a serious problem. We will also top of the line corrosion. This is an area that is still very, very challenging to mitigate using corrosion inhibitor under deposit corrosion, where you have scale formation and then you have corrosion with scale. So this is very challenging. Corrosion under insulation and green corrosion inhibitors. So normally green corrosion inhibitors, sometimes it works at low temperature, but the challenge would be developing green corrosion inhibitors for high temperature and high pressure conditions. Preferential well corrosion inhibitors are very scarce. So there are corrosion at these preferential wells. So this is one area of one area that is very important to look at. Now there are some research directions that I propose here: understanding pitting initiation and propagation, multifunctional corrosion inhibitors, galvanic corrosion inhibitors, ion carbonate and ion sulfide scale stability and their properties, synergy between CO2 and H2S corrosion. Just how do we develop inhibitor that can work in these two conditions at the same time? And then prediction of sweet and sour corrosion at high temperature and high pressure, and also performance of corrosion inhibitor at supercritical condition of CO2 and H2S. So these are some of the challenges that I have outlined here, because we know deeper and water wells available, they have very high TDS, high temperature, high pressure condition, high wall shear stress, CO2 and H2S. So how can we develop corrosion inhibitors that can meet this requirement? High shear corrosion inhibitor, high efficiency, exceeding more than 150 degrees Celsius, and high thermal stability, high persistency, especially for batch application, and also meeting environmental requirements, and compatibility with high TDS brine. So this is a huge challenge. So top of the line corrosion inhibitor, how do we develop a corrosion inhibitor that can be effective in the presence of acetic acid and can protect the upper part of the pipe, efficiency of like 90%. And this kind of model have appreciable vapor pressure because you need to vaporize and then protect the top of the pipe. So this is one of the conditions, and also it must have very high thermal stability also. So another important challenge for the future will be a corrosion inhibitor for high temperature acidizing oil and gas wells. So during acidizing, high concentration of mineral acid are pumped into the well. So, and this can lead to corrosion. So corrosion inhibitor is normally added. So how can we develop corrosion inhibitor that are totally green, more than 90% effective, and can protect up to 200 degrees Celsius and up to 1000 PSI or more? Could be effective in high turbulent flow or low turbulent flow conditions, high thermal stability. And these are some of the challenges that will need to be overcome. So in conclusion, I would love to thank industrial partners that support our research in the center, Saudi Aramco, KAUST, SIPChem, and SWCC. They have funded some of the projects that we have conducted over the years. And I will end here and entertain questions from you. Thank you so much.
Thank you very much, Professor Ime, for the wonderful presentation. Okay, the floor is open for questions. Please raise your hand and I will unmute you. Yes, Professor Philippe, please.
Yeah, well, thank you very much, Ime, for an interesting presentation. I was wondering what is your view on the possible use of reactive force field, because you mentioned DFT on one hand and machine learning on the other hand, but there are sort of two extremes. So how about some sort of intermediate approach using reactive force fields?
Yeah, excellent question. What I mean by yeah, I know DFT is computationally expensive, and you know, it takes a lot of time to simulate, especially when you have many atoms like periodic DFT. You need a lot of computational power to run such calculations, and also you need like smaller molecules you could do, but for inhibitor molecules that have hydrophobic chain, long chain, and the large molecules is very computationally intensive. So reactive force field is very good because it could, it could simulate electronic interaction too, and it will be much faster. And recently there is a DFT type binding, which is also very useful, and it gives accuracy comparable to DFT calculations, and it is mainly for large molecules and large surfaces. So this could help. Like I said, DFT will give you a descriptor. For example, adsorption energy. It is a descriptor for machine learning. So example, you could also use molecular dynamic simulation. It can provide you a descriptor like diffusion coefficient. So all these descriptors could be used to, as input parameters to learn and see which of the parameters is more effective in designing inhibitor. Because like we know, in real application, inhibitors are very, the system is very complicated. So for example, in the oil and gas field, you don't have only chloride. You have a lot of magnesium chloride, calcium chloride, a lot of ions in the brine. So it's not like only sodium chloride that you could easily run simple experiment in the lab. So the machine learning here will be like a tool that could help us to speed up development. Like for example, we have a lot of data in the literature, for example, in CO2 corrosion, for example. There are a lot of publications in the literature. For example, using azoles, what we could do, we could collect the data, and then we could compute these descriptors using this computational tool, like, for example, interaction energy, absorption energy, diffusion coefficient. We could compute log P. Log P is very important property because it talks about the whether the molecule has hydrophobicity on the, it gives you an idea of hydrophobicity of the molecule. Solubility is very important. And like I said, pKa value is very important because, it gives you a lot of information about the electronic ability of the molecule. So there are a lot of properties that you could compute and then use the data that you have, experimental data, and then train this data to be able to give you a predictive kind of information, which you could then use to do a fast screening, of new molecules that you could develop. So currently there are some few literature that publish this kind of information. But machine learning is a very good tool that we can adopt because doing computation is very computational extensive and then expensive. So it would take a lot of time to compute a lot of properties and begin to correlate with efficiency. So which is not really possible because even electronic property alone cannot correlate to inhibition efficiency. So you need a combination of properties to be able to describe inhibition of corrosion using organic molecules.
Okay, thank you.
Thank you, Professor Philippe. Dr. Zohair, I'm allowing you to talk. Please unmute yourself. Dr. Zuhair?
Yeah, Dr. Rami, thank you.
My pleasure.
I raised my hand for the previous talk.
Sorry for that.
I don't have anything interesting
Okay.
to talk, Dr. Rami.
Thank you very
Thank
much.
you.
Dr.
Thank you
Zuhair.
so much.
Dr. Johanna, yes, I'm allowing you. Dr. Johanna, unmute yourself, please.
Can you hear me now?
Yes, we can hear you. Please go ahead.
Okay. Actually, it is partly answered from the previous question. Very nice talk, Dr. Ime. It was very informative. My question is, like, in your approach of developing inhibitors, you were using computational design to select the active sites, the active. Is there any room like to do the same computational design for the chemical formulation of corrosion inhibitors, not only for the actives, but also the chemical formulations? This is my first question. So is there any room or any way in which we can employ some design so that we can select, like based on the design, we can formulate the chemical, not only the active. The other one, on the future approach, you just said that we will use machine learning, like to develop inhibitors. And as my understanding, the machine learning is semi-empirical or empirical model, which is based on data. So how can we know actually the fundamental mechanisms? Is there any way, like what is really going on the development? Can we know something? It is good for selecting actually the inhibitors, but is there any room to know what is really going on? Is there any way to understand the fundamental mechanisms based on the machine learning? Thank you.
Okay,
Dr.
thank you so
Ime,
much. Yeah,
Dr. Ime,
yes.
I'm sorry, but you have to be quick in your.
Yes,
your
yes.
answer.
Very
Please,
quick.
please.
Yeah, very fast. I will spend only 2 minutes. So, yeah, for the first questions, for any corrosion inhibitor development, the active is very important. So the active is the main ingredient here. So for the formulation, just adding something to improve the performance, like surfactant and the solvent for solubility, and then few things to enhance the performance. But the active is the major ingredient. So
okay.
So yeah. So for the second question, machine learning, good, is a semi-empirical approach. You cannot understand the mechanism of corrosion inhibition using machine learning, which is a mechanistic kind of thing. So you need spectroscopy, and then you need surface characterization, what Professor Marcus presented. So you need those tools also, like a black box. So after you could predict efficiency, you have to validate also too. And then you have to also study the mechanistic part using spectroscopy and then DFT and then other advanced surface techniques. Thank you.
Okay. Thank you very much.
Thank you very much, all. We move to our next speaker. We are proud to have with us Professor Neçar Merah. He is a professor in the Department of Mechanical Engineering in KFUPM. He completed his PhD in Mechanical Engineering from the University of Montreal, Canada. Earlier, he has completed his bachelor and master degree of Mechanical Engineering from University of Tulsa in USA. His research interests in fatigue of engineering materials and structures, alloy composites and nanocomposites, fracture mechanics and failure analysis, friction stir welding and processing, and finite element analysis. Professor Merah published many excellent number of papers in highly prestigious scientific papers and conference proceedings. The floor is yours, Professor Merah.
Thank you, Dr. Rami.
Please share, yes, please share.
I cannot start screen.
Please share. Yes, I stopped my share.
Can you see me?
Yes, just F5 to go to the full screen show mode.
Okay,
Excellent.
great. Let me get rid of this. Assalamu alaikum wa rahmatullah, and good afternoon, everybody, or good morning for those who are on the West Coast. My name is Neçar Merah, and Dr. Rami has just introduced me. Thank you to him. I am going to be talking about weathering effects on glass fiber reinforced composites and nano composites used in piping systems. The outline of my presentation will be as follows. I going to give a small introduction, but I'll make it short because most of my colleagues have talked about the different effects, especially for corrosion and other degradation factors. Then I will be talking about the weathering effects in two parts. Part one, it will be on glass fiber reinforced vinyl ester pipes and glass fiber reinforced epoxy. This is mainly a project that was done for Saudi Aramco about 10 years ago, and it is mainly qualification work that we have done. Then we'll draw some conclusions from the large amount of data that we had, but I will be presenting just part of the results. In part two, as a solution to some of the problems that we have observed, we are proposing to use nanoclay epoxy composite with glass fiber in order to improve a number of physical and mechanical properties. And then I will also present some conclusions related to part two. The applications of GFRE or in oil and gas, petrochemical, power generation, desalination, civil industries, and water transportation, raw and potable water, seawater, etc. The factors affecting the piping materials are usually the chemical factors such as oxygen, H2S, chlorine, and carbon solubility. Physical factors, our colleagues have talked about that, and temperature and pressure or physical factors. We have also biological factors, which are the biofouling, hard shells, plant life, etc. And the use of conventional materials in seawater of the Arabian Gulf and the Red Sea exposes it to high TDS, which is usually between 40,000 and 65,000 ppm, dissolved gases, organics, and other aggressive elements. All of these acting alone or simultaneously will contribute to the material degradation. And that has been explained very well by our colleagues in terms of corrosion. So the polymer-based composite pipes, they bring in high corrosion resistance, high strength to weight ratio, extended service life, design flexibility, low maintenance, long-term durability, and low thermal conductivity among the advantages. There are some disadvantages, as we will see in some of our results here. Composite materials are manufactured by many techniques, such as the hand layup and spray up, resin transfer molding, compression molding, centrifugal casing, vacuum assisted resin transfer molding, and filament molding. The pipes that we are going to be talking about are manufactured by filament winding process. As you can see here, this is the process that is used by bond strand and future pipe. They are winding the glass fiber at an angle of about 54.5 degrees. That increases mainly a number such as flexural properties of the pipe, and helps also in tensile properties. The objectives of the project that we had with Aramco 10 years ago was to look at the degradation of mechanical and physical properties of 6-inch diameter glass fiber reinforced vinyl ester. We have been provided with 2 batches of vinyl ester, one which we will call GFR-V1, and the second one we'll call it GFR-V2, and a batch of glass fiber reinforced epoxy, which will be exposed to wide range of harsh natural and accelerated environmental conditions. And we will be looking at how these environmental conditions are going to affect some of their mechanical and physical properties. These are the materials, the exposure conditions that we went through. That we used the outdoor exposure for 6 months to 54 months in Dhahran. We used the seawater filled and exposed to outdoor temperature. We use the crude oil filled and exposed to outdoor environment. And we use the seawater immersion that was done in KFUPM beach. I think we can see here Dr. Zohair and Dr. Faleh Sliman and the rest of us pushing this test facility into the waters here. So the duration, the first time every 3 months, we will pick up the parts and make specimens and test them. Then every 6 months, then every year after the second year. For the accelerated weathering, we have used only GFR-V2 and GFR-E. We exposed them to dry heat at 40 degrees in the environmental chamber and dry heat at 70 degrees, salt spray, UV in the environmental chamber, seawater spray, UV plus high temperature plus humidity in the environmental chamber, and oxygenated, 100% oxygenated seawater. And as you can see here, the duration of the exposure was 300 up to 10,000 hours. And every period of time, we will pick up the specimens that are ring specimens, and we test them. We look at the tensile properties, flexural, stress rupture, impact, low velocity impact, burst tests, fatigue tests, strain corrosion, cracking tests. We measure also the weight gain, glass transition temperature, and the cross-linking index. And we look at their microscopy, and we look at the fractured surfaces to see what are the mechanisms of fracture. All the equipment and facilities are available in the Department of Mechanical Engineering and RI that we used, and some of them actually we acquired just for the program, like the creep tester here, and we also designed and made a number of creep testers in order, because creep or the stress rupture takes a long time. So we had a battery of 5 creep testers that were used at the same time. So let me start with some results for GFR-V1. First of all, let's look at how the weather affects the color of the material. What you see here, you see the greenish, yellowish color of the as received pipe. After 24 months, you can see that it starts to discolor, becomes brown. And then after 54 months, you can see that fibers are coming out. So the layer of epoxy or the layer of vinyl ester starts to degrade. And here for UV exposure at 10,000, which is equivalent to about 36 months of outdoor exposure. We looked at the tensile strength of these vinyl ester specimens after 3 months of outdoor exposure, 6 months, 12 months, 24 months. And for outdoor, and then the oil-filled pipes exposed to outdoor conditions, and the seawater immersed pipes also after 12, 24, and 36 months. As you can see here, this is the baseline. This is the as received pipe. As you can see, the longer the exposure, the higher the tensile strength. So the outdoor exposure is actually improving the strength, tensile strength of the material. The same, you can see it for the oil filled, and to some extent also for seawater immersion. Why is that happening? We have observed that TG was increasing with exposure time. As you can see here, the blue diamonds here indicate the outdoor exposure without filling it with seawater. The squares indicate the seawater, the oil filled, and the triangles, the seawater field. You can see that up to about 36 months, the TG transition, glass transition temperature increases. That means that cross-linking, when we got it, the curing was not complete when we got it. We looked at also the cross-linking index, and we have seen that it increased. When we received it, it was measured to be about 84%. After 6 months, it went up to 93%. So curing was happening under the sun of Dhahran. And after curing, let's say between 24 and 36 months, you can see that degradation starts to occur. But still, up to 48 months, we still have the tensile strength, which is higher than the baseline, which is the as received material. We looked at the fractured specimens. This is the as received portion. You can see that there is delamination and debonding in this area here. After 36 months of outdoor exposure, you can see that there are matrix debris. That means there is brittle shear failure of the matrix and degradation of the vinyl ester matrix. And you can see that there are neat fibers, which are due to lower interfacial debonding. We have here the time to rupture, that is the stress rupture of GFR-V. We have observed almost the same trend where after 12 months, you have the rupture time higher than that of the baseline received after 24 months. But here there is so much scatter in the results that we believe that this is just the average, that it would continue also to increase after 24 months. With the oil field also showed that the same trend as for the tensile test specimens. And these are the fractographs. And we can see that after 24 and 36 months, we start having decomposition of the matrix. The stiffness, the flexural results, flexure strength, does not seem to be very much affected by the outdoor, the oil field and seawater exposure. And we believe that this is because of the helical winding of the glass fibers, which are oriented at an angle of maximum flexural stress, which is a combination of shear stress and normal stress. The flexure modulus was affected by the exposure to outdoor oil field and seawater. The burst test showed almost the same trend also for GFR-V1. You can see after up to 12 months, the burst pressure has increased also, and that is due to the fact that we have more cross-linking, the material has cured under the exposure. Now, let's look at the results of GFR-V2, which has a lower volume fraction of fibers. And this material, we have exposed it to dry heat at 40 degrees, dry heat at 70 degrees, humidity, 100% humidity, ambient temperature, humidity, salt spray at room temperature, oxygenated seawater immersion, UV, and UV plus high temperature. This is the baseline. This is the as received. You can see that dry humidity does not affect negatively the tensile strength. Actually, at 70 degrees, it seems like it is curing the material more and it's increasing its tensile strength. But humidity, salt spray, UV, salt water, etc., tend to reduce the tensile strength of GFR-V2. The impact resistance of the material, also you can see that for the deflection at peak up to 20 impact energy of 20, there is no effect of the exposure to humidity, salt spray, and seawater. As you increase the impact energy, it shows that humidity, salt water affect the impact, the deflection of the other. This is the deflection at the peak load. Now some results about glass fiber reinforced epoxy, which has a fiber content of about 60%. And these are the tensile. I'm having problem getting rid of this bar, this zoom bar. Any way I can get rid of it? The black bar.
We don't see it. We don't see it, Doctor.
You don't see it, but it's covering. It's covering.
It's covering.
It's covering my
it's blocking your side, huh?
Yeah. Anyhow,
you can just click the dash. You see the dash, the small dash.
The dash,
you can click,
okay.
Yeah, it will minimize it. Yes.
It doesn't.
You can move it away.
I will keep on playing with it up and down. Okay, so this is the natural weathering effect on tensile properties of glass fiber reinforced epoxy. And what you see here, the blue bar is the epoxy baseline as we received it. That's the tensile strength, the average. We usually test 3 to 6 specimens for all these. It took us 5 years and maybe 2 or 3 months in order to finish all these exposures and testing. So it is about 327 MPa. But after 6 months of seawater field and outdoor exposure, it reduces the tensile strength, reduces by 8%. After 12 months, it reduced by 12%. As you can see, this is different from vinyl ester. Vinyl ester pipes, the strength increased because it was cured. And here also maybe because epoxy is more hydrophilic and the water uptake, moisture uptake plasticize it and reduce its strength. The average fracture strain reduced even further. You can see that after 12 months, we have about 33% reduction. But the average stiffness did not reduce much after 12 months of seawater filled and outdoor exposure. We looked at the fractured surfaces, and we have observed this is the as received glass fiber reinforced epoxy pipe. We see that there is good interfacial bonding. There is interfacial debonding, and there is fiber breakage. But you can see that the fibers are well embedded into the epoxy. For 12 months exposure, you can see that there is a neat fiber pull out. There is a reduced interfacial bond strength for this area here. So there has been degradation of the interfacial strength between the fibers and the matrix. Accelerated weathering of GFRE. We put the pipe sections into salt water, oxygenated salt water, and we looked at the tensile strength after 300 hours, 1,000 hours, 3,000 hours, and 10,000 hours. After 300 hours, the tensile strength reduced by about 11%. Then up to 3,000 hours, there must, I don't know, maybe the water uptake was saturated. As we will see later on, there will be a saturation after a certain number of hours. And the maximum after 10,000 was a reduction of 13%. If you take into account the scatter, that means after 3 months, it seems like the water uptake has saturated. And we have the ingress of oxygenated seawater reduces the strength after 300 hours of the strength of GFRE after 300 hours by degrading the fiber matrix interfacial band binding. We looked at also at the stress rupture. We have developed an ST curve, taking into account the scatter, as you can see, of the data. We were able to just represent the behavior by this line and extrapolate it to 50 years of service. We have been told that this is the design stress for this type of pipe would be around 100 megapascals. You can see that at 50 years of service under stress up to 155, which represents about 50% of its ultimate strength, the pipe material can survive 50 years of use at room temperature. We have looked well also at the seawater film and the seawater immersion. And we can say that their presence reduces the life a little bit, but given the scatter, it's not very hard. It's not very easy to be conclusive. So this is about the stress rupture of GFRE. And let me conclude this first part, which was the work that we have done, part of the work that we have done for Saudi Aramco. Though there is evidence of weathering degradation of both GFRV and GFRE, they still exhibit long-term durability under the 15 environmental conditions. What I have presented here is only few of the results. Epoxy seems to be more susceptible to moisture, and its tensile strength and other properties degrade with exposure to water. So in order to improve the barrier properties of epoxy, we started looking at modifying the epoxy matrix with organically modified nanoclays. And that was another project that we got with CAXT and STIP. Nano composites, usually when you're using nanoclay was first practically used by Toyota researchers in the 1990s. They used it with nylon 66, I guess. But more and more it's being used with other polymers in order to increase their physical and mechanical properties. But distribution and mixing is very difficult to obtain. What we want to obtain is actually what we call the exfoliated structure, where you can see that each particle of the clay is separated by its neighbor by some of the polymer. If you don't mix it well, you will end up with intercalated nanocomposite or even conventional nanocomposite. In that case, you may even degrade the properties of your polymer. We, in the projects, actually two or three projects that we had, we looked at a number of mixing techniques, types of polymers, types of clays, and we looked at how we can get best clay dispersion and distribution. We looked at how to optimize degassing and curing process. The materials we used, actually not only epoxy, we have used also polyester. We looked at 3 nanoclays, 3 chlosides, and 3 nanomers, 6 types. We used high shear mixing and ultrasonication, coupled together or each by itself. And we used the IPDA curing agent, and we worked on degassing and curing of the materials. These are some XRD spectra that we have obtained for different clay loadings. This is the clay, the I-30 monomer clay. As you can see, it exhibits a peak at around 4 degrees.
Sorry, Professor Marah.
Or
the slide is frozen. I don't know. I'm the one who is frozen, or Dr. Ahmed, can you confirm?
Is it frozen?
Yes.
In at the XRD spectra? Anyone?
No, it's not there. You are in on slide 38.
38. What happened? What can I do, Dr. Rami?
Maybe
Should
you
I
can.
stop and
Yes,
come back?
maybe you can stop sharing and come back, please.
Let me, okay. A new share. Can you see it now?
Yes, yes.
Great. So I think I don't have to. Okay. So
Yeah, just move on.
yeah, let me move on. So we looked at different techniques, mixing techniques. We looked at different clays, different ways of making this, and actually we end up with 2 patents that for ending up with an exfoliated structure that you can see here. We were able to get mainly disordered intercalation and exfoliated structure every time we went through the process that we have designed. And exfoliated structure is what we want. The objective is to obtain a mostly exfoliated structure. Once you have this mixture of intercalated and exfoliated structure, you can see the effect of addition of nanoclay on your tensile strength. For example, here with 1.5 or 1% of nanomer addition, we have increased the tensile strength by about 10 or 11%. After that, once you go beyond 1.5%, we have done other things with 1.5, it starts to decrease. That is because of the presence of clustering of nanoclays and the presence of voids. Actually, we were not able to obtain exfoliated structure after 2% of the nanoclay loading. But up to 1.5, the tensile strength was improved, and the flexural strength also was improved up to 1.5. You can see this is about 14% improvement in the flexural strength. If you look at the fracture surfaces, you see that the neat epoxy has a smooth, brittle cleavage type fracture. The nanocomposites are rough and corrugated surfaces. And for 5%, you start seeing voids and clusters of nanoclays. So that is the material that becomes now our new matrix. We started looking at how the water uptake is affected by the presence of nanoclays. We looked at the percent weight gain as a function of time, of square root of time in hours. And you can see that this is the red squares here or for pure epoxy. You can see that after, this is about 300 days of exposure. It goes, it increases, the weight increases by 2%, 2.3%. But the addition of 1% clay reduces the water uptake. And you can see also that the water uptake starts to saturate around 200 days of exposure to, this is tap water actually at room temperature. If we look at the diffusivity and the maximum weight gain with clay loading, you see that the diffusivity decreases rapidly after 1% of clay loading. The maximum weight gain also decreases, and after around 4%, the behavior, actually there is so much scatter here. It seems like it is saturating after 3%. So the presence of clays, especially in the exfoliated structure, reduce diffusivity and reduce the maximum water uptake. And how does that affect the tensile strength and the modulus of elasticity? We looked at the tensile strength. You can see before and after 1%, well, this is the same result as we have seen. But what if we expose it to water? You can see that if we expose it to water, you see the blue line here, there is also an increase in strength due to the presence of 1% clay. And also the crude oil, you can see the crude oil affects less the behavior of the material because the ingress of the crude oil is little compared to that of the water, maybe because of the molecule of the crude oil which is large. The same thing you can say about fracture strain here, and because we are maybe running out of time, let me move to the glass fiber, the hybrid glass fiber nanoclay composites. This is another project that we have done. We have made a hybrid nano composite. That means the matrix here is not the epoxy by itself, but it is epoxy with nanoclay. And we used hand layup and pressure. We used chopped strand mat and fibers at a volume of 30%. And we looked at the flexural strength of the glass fiber and how it is affected by the addition of nanoclay. This is the epoxy. This is the glass fiber reinforced without nanoclay. This is the glass fiber reinforced with nanoclay, which we call the hybrid nanocomposite. You can see that after adding 1.5% of nanoclay, we increased the strength of the glass fiber epoxy by 11%. Going to 2%, we still have like 8%. But as you go down, as you go higher and higher, because of the presence of clusters and stress razors, the strength, flexural strength reduces. The same thing can be said about the flexural modulus. 1.5 increases the flexural modulus by about 14%. So we can say that nanoclay generally result in improvements in strength of stiffness and stiffness of epoxy glass fiber material. Why is that? As you can see, this is 0% clay. You can see that the failed surface has a neat and loosely held fibers. But with 1.5%, we can see that the increased fiber matrix adhesion. As you go into 3%, you go back almost to the same behavior where we have neat fibers. 5%, we start having clusters and voids, which reduce the strength of the material. We looked also at the impact behavior, and these are some of the results. Again, here, the exfoliated structure has a higher peak load, less peak deflection, and absorbs less energy under impact. Physically, this is what we have observed. These are the areas you can see for the impact energy of 10 joules, 1.5% of clay improves damage by 31%, 3% by 25%. Under 20, we have even higher improvement, but at 35 joules, this is the threshold impact energy. After starting at 35 joules, we start having breaking or penetration of the top into the material. Finally, we looked at the effect of temperature and water on the diffusion rate and the maximum water uptake. You can see that at 80 degrees, the diffusion rate is a lot higher than at that room temperature. The maximum water uptake is higher also, which we will see as a result on the flexural strength, that the presence of water reduces the flexural strength. And water at high temperature, the immersion into water at high temperature reduces even more the GFRE. This is the GFRE. This is GFRE with nanoclay. First of all, you can see that there is an increase in the strength as you add 1.5%. It goes from 209 to 233. And even when exposed to water for 4 months, it's still the strength, the flexural strength is still higher than that of the GFRE without nanoclay. So again here, this proves that the nanoclay really improves the flexural strength of GFRE, and the flexural modulus also, we can see the same story about the flexural modulus. Finally, we conclude, this is for the second part, that addition of nanoclay to epoxy improves its moisture barrier at room temperature and high temperature. Exfoliated structure was obtained for clay loadings between 1% and 2%, and these resulted in optimal mechanical properties. Higher clay loadings result into agglomerations and voids, which make them lose their reinforcing ability. Glass fiber reinforced epoxy with nanoclay has more addition to the fibers and increases the stress transfer capability. Superior compression strength of clay improved the flexural properties, and also the flexural properties were mitigated. I mean, the damage was mitigated by the presence of the clays, because they create a formation of tortuous fracture paths, and they result in lower energy absorption under low velocity impact. I would like to acknowledge the support of King Fahd University, Saudi Aramco, Jana provide us with the epoxy, Amiantit Bodstrand provide us with a number of pipes, Future Pipe, Caxton STP, and my colleagues, some of them are still at KFUPM, some of them are outside KFUPM, and the students who did the work on these projects. And finally, thank you. And if you have any questions.
Thank you very much, Professor Merah, for the wonderful presentation, very informative. Due to time constraint, we have the chance only for one short question. So who would like to take this chance? Please raise your hand. Okay, I'm sorry, I'm giving the chance to Dr. Hakim.
Assalamu alaikum, Dr. Neçar Merah.
Very short question, please, Dr. Hakim, please.
Yeah, thank you, Dr. Rami, for giving me the opportunity. Thank you, Professor Merah, for the very nice presentation and very, very informative. I just want to ask, maybe I have couples of questions, but maybe I can discuss some of them with you, maybe during the discussion panel, or sometime I can try to meet you, because I'm also trying to work on something similar using waste material. So I was thinking that your experience from this very intensive project might be very useful and helpful. But my quick question here is just, do you think that there are ways by which the mixing of the nanocomposites, nanoclay can really help improve, the amount? Because I can see that you're still, if we look at the cost of the nanoclay and the percentage improvement that is adding, I don't know how we can really justify that amount of improvement. Is there a way by which we can basically improve the dispersion of this nanoclay so as to improve further these mechanical properties you have obtained, especially using model as an advanced method of mixing and dispersion? This is just a question. Thank you.
Thank you, Dr. Hakim. Yeah, actually the nanocomposites now are used at the industrial level. They are in aerospace, they are in automotive industries, they are they have not only, you know, the mechanical properties improvement, which we're talking about 14 and 11% and 20%, but the barrier property, the gas barrier and the moisture barrier property and other agents barrier property, those are very important. If you combine that with an improvement in mechanical properties, you have a winner. You have to look at them as coupled with the barrier properties. The fact that they resist to gas and moisture diffusion, and at the same time improve the mechanical properties.
Mm.
But if you're doing them just for mechanical properties, maybe may not be very economical to do that.
Thank you. Did you have an experience testing for the gas? Sorry, Dr. Rami, I'm asking this question.
Okay, do it.
Do you have an experience in testing the gas, you know, like CO2 penetration and things like this?
No, but I know a lot of people who have done it. Yes, actually, first project was supposed to be with Aramco for gas permeation, but unfortunately, it didn't go through because the person responsible from Aramco left, and so yes, it's actually, yes, there is a lot of people, there is a lot of researchers doing that.
Okay, thank you, Professor. Maybe I will have to meet you sometime. I will have a lot of other discussion with you on this. Thank you, sir.
Okay, thank you, guys. Thank you. I'd like to apologize for Dr. Kumar. Sorry, I cannot take your question. Maybe you can post it on chat, and I'm sure Dr. Merah will answer you in the chat. Due to time constraint, we have to move on, but we will take break for 10 minutes. It's 5:10 now, so 5:20 we will meet again. 5:20. Thank you.
Thank you.
Assalamu alaikum. I think we took more than 10 minutes as a break. I have one announcement. Unfortunately, Professor Digby McDonald, he couldn't make it to join this event. He just informed me that he has some technical issue connecting to internet. So the change we have, it will be a little short change in the time, because we are supposed to start the panel discussion at 17:45. So now it's almost 17:30. So I think we can move on to the panel discussion that will be moderated by my colleague, Dr. Fadi Badur from Mechanical Engineering. Dr. Fadi, are you ready? Dr. Fadi? Dr. Fadi?
Yes, thank you, Dr. Rami.
Yes.
It was the mic was not active, so now thank you for activating this for me. Okay, Bismillah ar-Rahman ar-Rahim. I'd like to welcome you all. Good evening, gentlemen. Assalamu alaikum wa rahmatullahi wa barakatuh. I would like to take this opportunity to thank our speakers. And this is going to be our last activity in this forum, started this afternoon. And I would like also to extend my thanks to our audience who spend the time with us. So my name is Fadi Al-Badur. I'm in Mechanical Engineering Department. I'll be the moderator for the panel discussion. And also Dr. Hakim from the Center of Advanced Material will be with us as well. This evening, we'll be talking about a very important topic related to the economic and technical impact of materials degradation. And today, the discussion will extend to also the impact and the environment and especially if you recall by the opening remarks from Dr. Ahmed that corrosion cost, for example, in Saudi Arabia reached above $20+ billion. These in terms of direct and indirect costs. So I would like to welcome our panelists who are members of the speakers with us. I will start with Dr. Philippe Marcus, Professor Philippe Marcus, Professor Neçar Merah. And also we'll have a new member on the panel. Was not one of our speakers today, but we'll have Dr. Zuhair Qasim, and also we'll have Engineer Oscar with us as well. So to start the discussion, I'll be asking some questions that simply covers the theme of the discussion today. And after that, in the other half, I will keep the floor open for the audience to ask their questions. I would appreciate sending the questions through a question and answer button on the Zoom meeting. Also, Dr. Hakim will be, inshallah, following up these questions, and we'll put them into order to the members on the panel. So I would like to thank you again, and I would appreciate, Dr. Rami, if you have activated the mic for the members.
I think the mic is active for all members. I think Dr. Zuhair also.
In the panel.
Yeah.
Okay, very good. Thank you very much. Thank you very much. Okay, I will start with my first question because we're talking about the economy. So I would like to, and technical issues, I would like to present my first questions to Prof. Philippe. Can you hear me, Prof. Philippe?
Yeah, yes, very well. Yes, very well.
Yeah. So I would appreciate if you can shed the light a little bit about the technical impact of material degradation and the recent innovative solutions. So from the technical aspects.
Okay, I have prepared one or two slides that I can show to initiate the discussion on this topic on the technical impact. So Rami, can I share the?
Yes, please. Yes, you can.
Okay. Yes, so well, just a brief introduction, because I think everybody now knows about that corrosion is a degradation phenomenon by which solid materials, including metals and alloys, and of course I'm more specialized in metals and alloys, but other materials have been presented today. They lose their integrity and properties as a result of the chemical or electrochemical interaction with their environment. And technical impact is now what I'm going to talk about. Corrosion is a major problem for our advanced society as it affects numerous technical fields where metal and alloy components and other materials are used for their structural and functional properties. And I have just listed a list, which is not exhaustive, of areas where corrosion is very important: energy production, transport, oil and gas and chemical industries, infrastructures, like roads, bridges, but that could even include transport also of gas and oil. Biomedical implants should not be forgotten, because even if it's small in tonnage, it's big in importance. And even in the microelectronics industry, there are major corrosion problems, and there are actually new corrosion problems that appear due to regulations on the use of chemicals. So chemicals have to be changed, and this causes problem, for example, in the chemomechanical polishing of semiconductors. So now talking really about impact, I'd like to present this slide, which can be used as a basis for a discussion, that the failure of metallic structural components, but it would be true also for polymers and or concretes or composite material, can have dramatic consequences. One of them is the most obvious one, is that the performance and the service life are reduced by corrosion, and we have already heard this number, which is fairly widely accepted, that the direct cost of corrosion amounts to about 3.5% of the gross national product. And as far as I could see for Saudi Arabia, it seems to be maybe even higher, but I don't know if it was only direct or both costs, but this is for the direct cost. Now, of course, there are other impacts that are related to technical problems. The safety can be compromised in fields where safety is a must. And I'm, of course, thinking in priority to the aeronautic industry or the nuclear industry, where there is absolutely no room for any failure. Of course, this would be true for the oil and gas industry, but I think that safety is maybe even more important, if I could say so, for an airplane or nuclear power plant. Now, the environment can be put at risk, and this is true, for example, for oil and gas transport. If there's a failure due to stress corrosion cracking, for example, or fatigue corrosion. And of course, health can be at risk via contamination of the environment, but also for metallic bio implants. Corrosion of materials implanted in the human body is obviously not something that we want to face. So just the third slide that can be used as a basis is what can we do? So what are the possibilities? Of course, we can design new materials, and there I could give as an example high entropy alloys or multi-principal component alloys, as we call them now. They are materials that have 4 or 5 alloy elements. They are known to have improved mechanical properties. Their corrosion properties are not yet very well established, but there is an intense research in this area. So this area where there are lots of scientific publications. We can, of course, also design new inhibitors, and we have had a talk on that today, new inhibitors. And there we have also to take into account environmental considerations. So green inhibitors, or at least environment-friendly inhibitors. We can design new coatings, and I'm thinking, for example, of new conversion coatings. And there, the driving force really are the regulations. You know that in Europe and also in the USA, the use of hexavalent chromium will be banned. It is already banned for some industries, not yet for the aeronautic industry. And there is an urgent need to use hexavalent-free conversion, hexavalent chromium-free conversion coatings. And of course, cathodic protection is an area where there are a lot of new developments that are important, and also areas where cathodic protection was not used in the past and is more and more used, like, for example, in harbor infrastructures. So for all of this, I would like to state, but it's of course because I come from academia, but I'm convinced that fundamental research, meaning their low TRL research, is needed for a rational design, meaning knowledge-based design of corrosion mitigation solutions. So this is a brief introduction where I tried to cover what are the main technical issues in which industrial areas, what are the ways to mitigate corrosion by new materials, new inhibitors, new coatings, cathodic protection. And also I took this opportunity to emphasize the importance of basic research. And of course, this has to be coupled to applied research to develop new technologies. So perhaps this can be used as a basis for the discussion.
Thank you, Prof. Philippe.
Yeah.
I would like to ask Dr. Zuhair. Can you hear me, Dr. Zuhair?
Yes, yeah.
Dr. Zuhair, currently the kingdom is proceeding in the Vision 2030 and trying to target localization and diversification of economy. And we'd like to give us your point of view about the role of localizing innovative solutions in the economy, especially related to the material degradation.
Thank you, Dr. Fadi. I prepared 2 slides, if I can share it with you.
Sure. Dr. Rami, could you please allow Dr. Zuhair?
Yes, please, go ahead.
How can I share it now?
It's not shared, Doctor. Go to share screen.
Share screen. It's not showing up here. The whole thing is not shown in your chat. I don't have the full option of Zoom. What should I share screen?
Share screen, yes.
Share screen, yes. Okay. It's not active.
I think Dr. Rami should make Dr. Zuhair as a speaker.
I cannot do it. Actually, this should be defined by the system. Can you send it to me, Doctor, by email?
طيب خلاص I'll talk briefly يعني.
Sorry for that. Sorry for that.
I'll talk briefly. I just want to highlight that the only study that I have seen about the cost of corrosion and material degradation in general was done by CSD in Aramco. It was published in 2006, and the total cost was around $900 million per year, so almost $1 billion per year. This was in 2000. Was published 2006. I think the study was done over 2-3 years, 2003 and up to 5. And the final conclusion they mention is that there is an opportunity to save at least 25% of that just by using the current technologies available to Saudi Aramco. So we know that Saudi Aramco is the one of the most advanced company here in Saudi Arabia. I would draw the same parallel conclusion with other companies which are less qualified as Aramco. So I will go also to the study published by NACE in 2002. They did the most inclusive study for the cost of corrosion in 1998, and they come up with this magic number, 3.1 GDP. And at the end, they mention some strategies where how we can save and reduce the cost of corrosion. And they have two categories. The first one is technical preventive strategies that we have to, companies, they have to cooperate with a research center, with universities, and provide advanced techniques, advanced design practices, advanced life prediction models. So this collaboration should continue for research development between industry and research communities. And the second category is very obvious, and it focuses on awareness. That we need to increase awareness of corrosion to the public and to the industry. Change the misconception that nothing can be done about corrosion. Many people in the industry, especially that small and medium companies that do not have full staff trained in corrosion, so they will surrender to corrosion. They wait for some part to fail and then replace and move on. So this costs a lot, and if small investment on educating the staff about available technologies, it's not something that is well established, and this can, of course, reduce the cost of corrosion. And the universities, as we are doing in our department and in chemical engineering, we are teaching our engineers, although it is an elective course, undergraduate, graduate courses as corrosion science and engineering. And but lately we are not offering short courses for people who did not have a chance to study corrosion in their formal study. I think this is a venue to open to educate the staff in corrosion. My last comment is about the current status of technologies to fight the cost of corrosion. Protective coatings is the most common technology, and we have active research in the center here on coatings. We also need to improve and increase the collaboration between the industry and academia and research center to develop coatings for special weathering in Saudi Arabia. So most of the coatings come from abroad, from North America, from Europe, which are developed for a specific environment. So we need to localize this more. I'm not aware of any industrial scale center for coatings research in Saudi Arabia. The second technology, corrosion resistant alloys, stainless steel. This afternoon, Professor Philippe does very fundamental study about how stainless steel corrode. I think we need also to translate this knowledge to the industry and to utilize these corrosion resistant alloys as effective as possible. Corrosion inhibitors, the center has been doing excellent job to collaborate with many companies, especially Saudi Aramco, to develop special inhibitors for a special application. I think this is great, and we should continue along this road. But we need to localize manufacturing of these inhibitors. And so if we develop some chemicals that are active inhibitor, we should look for a way to the industry invest more money on developing these inhibitors locally. Number 4, the technologies that are effective in resisting corrosion is the composites, and Oscar, Dr. Merah discussed this a lot. And I'm very glad to share that Aramco has invested a lot of money to build the center, composite center, I think, in Spark, Medinat al-Malik Salman, city of King Salman for energy here nearby gig. I think they are about to produce now some of their products, composite pipes. So this is what we mean by localization. That these, since as we have seen from the nice presentation by Oscar from Aramco, how composites can improve corrosion protection or reduce corrosion costs. So the Aramco put a lot of investment to build this center to manufacture reinforced thermoplastics. And last time I was talking to someone, he said maybe either it is in production phase or it's about to do that. So this is my my main thoughts, Dr. Fadi.
Thank you, Dr. Zahir. Thank you. for your information. And we would like now to open the floor for the audience if they have any questions.
Okay, please.
Dr. Hakim,
raise their hand, and I will allow.
I think there are some questions from the audience. Dr. Hakim mentioned.
Yeah, there are a few numbers of questions here, and also there are some questions during the presentations that were not attended to, maybe due to time. So I'll start with this question here. There have been a lot of discussion on corrosion as a main mechanism for material degradation. So this question is asking, what are the other types of material degradation that has significant or has good impact on the economy? Or is it only corrosion that is that's the main mechanism for material degradation? So this is the question. I think this would go to any of the panelists and they can give their own view to this question. Maybe Professor Marcus can try that, can start from the academic point of view.
Okay, well, usually it's considered that materials can fail due to either mechanical failure in the presence of load or stress, or by chemical interaction with the environment. And of course, the combination of the two is a major problem. That is stress corrosion cracking, where there is an sort of amplification of the effects of the corrosion if there is applied stress or corrosion fatigue. If you take the example of failure in the materials in nuclear power plants, for example, it's considered that most failures are related to corrosion, and in particular stress corrosion cracking. So each time you have a corrosive environment, you may have corrosion. You may also have stress corrosion fatigue or stress corrosion cracking or fatigue corrosion. So I would say, and I think if there are mechanicians here, they will, I guess, argue that failure due to just mechanical properties are important. And I would like to add to that failures due to combined mechanical load or stresses and chemical interaction with the environment. And that's why I think it's important also in education that the students learn not just chemistry or not just mechanics or mechanical engineering, because there are many cases where in the industry where engineers are needed with expertise in both chemistry and mechanics. And usually it's considered that students in chemistry don't like mechanics and vice versa. So I think we have an effort to make to educate young students, because the industry needs this kind of expertise.
Thank you, Professor Marcus.
May I add something here?
Yeah, Dr. Zain, please go ahead.
Yeah, I agree with Professor Philippe about combining chemistry and mechanics. And also, I would like to mention that one of the main form of failure is due to wear of materials. Yeah. Rotating equipment, they are subject to fatigue, fracture, and wear. So although corrosion is the main mechanism, but we also have mechanical wear is also a big problem in the industry. And fracture and fatigue. These are the three main mechanically. And if you, as Professor Philippe pointed out, if you add a corrosive environment at the same time, it will the damage mechanism, the aging will be much faster.
Thank you both. I think from here we can, I don't know if Professor Merah is with us, Dr. Nasser. Are you still with us?
I think Prof. Merah has left. I think he because he sent me a message. He excused. He has another appointment. Do we have any other questions on the chat?
This is a question related to what Engineer Oscar has just pointed out regarding the UV resistance of nanocomposite GFRP, composite material that he just discussed about. So the questioner is asking if they actually did a kind of UV resistance test. So I think that can be discussed sometime later.
We can also accept direct questions from the audience.
Yeah.
Please, you can raise your hand and then we'll open the mic for you.
Yes, I have a question. I'm just trying to find where I raise the hand, but you allow me.
You don't need, Dr. Ahmad, just go ahead.
Okay. So I just have a question just for Professor Phillips. Okay, Professor Phillips, you are saying that the passivation, the thin film oxide layer that form on the stainless steel or any other material started as an amorphous, and then with time it become more of crystalline. Do you have any idea what the crystal structures, and is there any relation between the crystal structure of the thin film, the chrome oxide, for example, compared to the stainless steel, or there is no relation between these two?
Yeah, yes, there is. We found they are extremely thin oxide layers, so that's why we used scanning tunneling microscopy. The only other technique would be grazing incidence X-ray, but that requires the use of a synchrotron because classical X-ray, even low angle, is not sensitive enough. But using STM, it has been demonstrated, and some work by X-ray diffraction on synchrotron have confirmed that the passive film is crystalline, and the structure is the structure of alpha Cr2O3, but of course it's not pure chromium oxide. Alpha Cr2O3 it's the corundum structure, but of course there is iron. There are iron cations in the oxide, and yes, there is a relationship between the structure, at least the match between the crystal structure of the oxide and the base metal is important, and very often the direction of growth of the oxide is governed by the fact that the most stable oxide is the one that has the lowest surface energy. And then there is another point, which is the interface energy, which is minimized if there is a good epitaxy between the oxide and the substrate. Of course, at the moment, it's not easy to make some sort of engineering of this, contrary to the electronic industry, where they have been able to optimize these structures because it's on small areas. I mean, doing a wafer is not like rolling stainless steel. But I think in the future there will be progress by engineering this crystallography. Similarly to, I had a question on grain boundaries after my talk, and yes, indeed, of course, grain boundaries are important because they may be selective areas for the initiation of localized corrosion. But there again, we need more data because it depends very much on the exact structure of the grain boundary. For example, twins that we find in austenitic stainless steel, because they have an face-centered cubic structure, twins are not sensitive to localized corrosion, but high-angle grain boundaries are very sensitive.
Thank you, Professor. One other follow-up question that I just had in mind when you were discussing the issue of passive film is, have you experienced the formation of an amorphous film on any of the materials? Or is it possible to engineer an amorphous film on this stainless steel? And which do you think will perform in terms of corrosion protection more better?
Well, I think that crystalline films are just as good as amorphous films. The reason why some people have claimed that amorphous oxides are better is in fact because if you grow oxides on a substrate which is amorphous, you may have an amorphous oxide, and very often these materials will have maybe less impurities. So it's the case, for example, there is a lot of activity, for example, on stainless steels that are processed by 3D machining. So there it's important to exclude the role of inclusions before looking at this effect. But in the absence of inclusion in the material, crystalline oxides, I think, are even better than amorphous films. So I would not recommend to find a way to make films amorphous because they naturally are crystalline and they are better when they become crystalline. There might be an exception, which is aluminum. We have not done the same studies on aluminum, and it might be that there the passive film is amorphous. On the other hand, pure aluminum is quite resistant to corrosion thanks to this oxide layer. But as you know, the problem with corrosion of aluminum alloys is more related with the intermetallics than with the aluminum itself.
Thank you, Professor. There's a quick question here to Dr. Zuhair. The questioner is asking, the $900 million you mentioned in your comment regarding the cost of corrosion, and he's asking, is it specific to Saudi Aramco or Saudi Arabia specifically, or is it a global amount?
No, actually, it was mainly about different plants and operation in Aramco. So it is the cost of corrosion in 2004 or 5. So it is only for Aramco, Saudi Aramco.
Thank you for that clarification.
If there is no further question, I had a question for Professor Philippe. I did not have a chance to ask him this afternoon. Can I ask him?
Yes, go ahead. It's the time. It's the right time.
Professor Philippe, when you show the oxidation of stainless steel and the formation of islands of iron oxides, which degrade the corrosion resistance, localized corrosion resistance, this is done in dry corrosion. When you have, for example, fracture in corrosive environment, and you have new fresh surface, and this electrolyte comes in contact with the surface, do you think the same thing happens, the formation of chromium oxide, mixed oxide, or because of thermodynamics favor chromium oxide, it will be first form, and maybe with time, then you have this formation of islands. So my question is, when you have fresh surface in electrolytes, whether it is acidic or alkaline, is it first would be chromium oxide will be perfect structure, or it will have the same defects?
Well, it's a good question. To look at so early stages as I have shown today, so far it's possible only if you start with a surface prepared in ultra high vacuum, because it's the only way to start with a completely metallic surface and then be able to follow the oxidation layer with a high resolution. So I cannot answer your question from the basis of experimental work, because I think no one has done it. Of course, it's possible to produce a clean, fresh surface, and by, for example, the guillotine system that Tim Bernstein used many years ago, but then you cannot look at the film with good resolution. So it can only be a guess. So based on what we have done, I would guess that yes, the early oxidation stage will be the oxidation of chromium. Now, whether it will be crystalline or not, that remains to be studied. Because usually to get a fresh surface, as you described, it means that either you scratch the surface or you crack the material, which means that the fresh surface exposed will have a very high concentration of defects. So there may be a lot of nucleation sites, which would be equivalent to the steps that we are looking at. Because if you scratch or if you crack a material, you will produce a high density of defects looking like steps. So to make a long answer, sorry, short, yes, I think that chromium oxide will be formed first also in that case.
The reason I'm raising this because, you know, the hydrogen economy is around the corner, and people have huge interest in pipelines and to transmit hydrogen. And stainless steel is the most candidate material for that. And I'm working on hydrogen embrittlement of austenitic stainless steel. And I'm just wondering how, when you have fresh surface, you'll have this adsorption of hydrogen at the fresh surface and absorption also, the fusion in. So maybe the kind of the oxide film that builds during the cracking is also defective at allowing hydrogen to be absorbed. I think this will be interesting, maybe collaboration if we have some fresh surface and introduce hydrogen gas and see how the isotherm of this hydrogen gas and what is the defects in the oxides that allow hydrogen to be absorbed. There is huge interest in this about hydrogen embrittlement of stainless steel.
Yeah, it's a very interesting point, and actually, thank you for bringing up this point. I think in the future, this point you are talking about will be very important, because if we switch to a hydrogen economy, it means there will be thousands or hundreds of thousands of pipes transporting hydrogen, and that will be a major issue. There are already lines transporting hydrogen in some factories, so they have some experience on that. But what you are talking about is actually a major issue, and I think that's precisely an issue that requests very basic research, because most people, I mean, most scientists don't really know. If you ask the question, even the role of the oxide in the entry of hydrogen, can we completely block entry of hydrogen if there is an oxide, or what are the kinds of defects that could allow hydrogen to penetrate? There is no clear answer. And then the next question is the one you ask, if locally there is the oxide is ruptured. I would say this will depend on the relative kinetics of formation of, if it's stainless steel, it will depend on the relative kinetics of formation of the oxide layer with respect to the dissociative adsorption of hydrogen. And this is not known to my knowledge.
Thank you, Professor. Thank you for the nice, thank you, Dr. Zouhair. I don't know if you have further questions, Dr. Zouhair.
I would like to thank Professor Philippe. That was really a nice opportunity to talk to him.
Yeah, thank you.
Thank you, Dr. Zouhair, for
it's a very interesting subject.
I think Dr. Hakim, I'm sorry,
yeah,
because we have to, stick to the time. So I think, I'm sorry, we need to end the panel discussion and give the chance for Dr. Ahmad to give his closing remarks.
Okay, thank you.
Thank you.
Thank you. Thank you very much. And now the floor is for Dr. Ahmad.
Okay. Thank you. Yes, I would like just to thank actually all of you for attending the workshop, for the fruitful discussion, exchange of ideas, and the and a special thanks for the presenter, the distinguished speaker, Professor Phillips, Mr. Oscar, Dr. Ime, Professor Neçar Merah, and also the participation from Dr. Zuhair in the panel. Yes, it was an excellent forum. Okay, this is our first experience for online forum, and I think it was very beneficial. I learned a lot today, this afternoon, and we are looking for more forum in next year, which will be after 3 days. We will have next year, so we will arrange our next forum, and yes, we are looking for your participation again with another interesting topics. Yeah, okay. Thank you again, and I hope we'll see you later in the next events.
Okay, thank you very much.
Thank you.
And it was a very interesting forum. So congratulations also to the organizers and to the speakers and to the audience for the many good questions.
Thank you, Professor. Thank you all participants.
Thank you, Professor Philip. Thank you, Engineer Oscar.
Thank you, Engineer
Dr.
Oscar.
Zuhair. Thank you all, guys, and hope to see you soon.
Okay, thank you.
Thank you.
Bye-bye now.
Thank you, Dr. Zuhair. Thank you.
Thank you.
Thank you, everybody. Bye.
Assalamu alaikum wa rahmatullahi.
Bye-bye.
Salam wa rahmatullah.
Assalamu alaikum.